Example 2. Identify the vertical asymptotes for each function and state the domain of the function. We know that when we have rational functions, the denominator cannot be equal to 0. So looking at this first example A, we want to know, when does the denominator equal 0? Let's see. X plus 2 equals 0 when x is equal to negative 2. So that is what's going to be our asymptote for this function. Those are the places that the domain doesn't exist. So when we write our domain, we'll write the set of all x such that x does not equal negative 2. We can allow any other value of x, but not negative 2. In interval notation, we can write this as the set from negative infinity to negative 2, and then from negative 2 up to positive infinity. Let's go look at the graph and verify our thinking about this problem. The blue part is the graph that we were just looking at, x minus 1 over x plus 2. And we found that x equals negative 2 is our asymptote. And that matches up with what we're seeing in the graph here. We can see that as we approach this line, x equals negative 2 from the right-hand side, the y values are going down towards negative infinity. And then as we approach over here from the left-hand side, the y values are going up towards positive infinity. Looking at example B, the denominator of this function actually can be factored. Let's see, this is x plus 1 times x minus 1. We have an interesting case here because the factor that we're getting in the denominator actually can cancel with the numerator. So this simplifies to 1 over x minus 1. But in the original, that factor that I canceled, we have to still keep track of that number because it's something that's not allowed in the domain. For our domain for this function, x cannot be equal to positive or negative 1. We're seeing that from the factored version. But let me write this in interval notation first. Let's see, from negative 1, and then negative 1 to positive 1, and then 1 to infinity. But it turns out that we only have one asymptote. We only have one vertical asymptote. And that comes from the final simplified version. Our asymptote is x equals positive 1. That's the only one that we have. But that negative 1 is going to show up in the graph as a whole. That negative 1 is not allowed to be plugged in for x in the original function. So what I'm going to do is I'm going to take the value negative 1 and plug it into this. Let's see what happens if I find f of negative 1. Well, that'll be 1 over negative 1 minus 1, or 1 over negative 2. What happens for this particular graph is we have a hole when x is equal to negative 1 and y is equal to negative 1/2. So that's another discontinuity in the graph. We call that a removable discontinuity. Let's look at the graph and see how this is, what this is looking like. Here's the graph of the function we were looking at, x plus 1 over x squared minus 1. And as you can see, there's only one asymptote. It's here when x is equal to positive 1. And then here's that hole that we were talking about. When x is equal to negative 1, our y value is negative 1/2. So this is matching what we saw in the algebra. Looking at example C, the denominator here can be factored. The numerator can't be factored, so we aren't going to have a situation like we did in example B where there's possibly a hole with factors that cancel, because the numerator, because it's a plus 4 there, we can't simplify that. So let's just think about x squared minus 2x minus 8. When does that equal 0? This factors into x minus 4 times x plus 2. So our asymptotes are x equals 4 and x equals negative 2. The domain for this function is the set of all x such that x does not equal 4 or negative 2. And then in interval notation, from negative infinity to -2, we always want to put our numbers in order as they show up on the number line. -2 to 4, and then 4 to infinity. Let's fix that because that looks messy. All right. Let's look at the graph. So this is a little bit more complicated of a graph, and we can see that we've got two asymptotes. I've got something else turned on here. That's from the last graph. Yeah, we can see that we've got asymptote there at -2, and then also at 4. And the different components of the graph are getting more complicated as we have higher exponents in the graphs that we're looking at. And then for our last example, that denominator looks pretty complicated. It's to the 4th power, but it looks like it's a quadratic in disguise. It has the same structure as this, and we know how to factor that into x minus 4, x minus 1. So the numerator, let's see, no, the numerator cannot be factored, so we don't need to worry about that. There's nothing that's going to be canceling. So let's see, let's set, this is going to be x squared minus 4 and x squared minus 1. This is this denominator here. That can be factored further into x plus 2x minus 2, and then x plus 1, x minus 1. So in this case, it looks like we've got 4 asymptotes. -2, +2, -1, and +1. For our domain, x, oops, x cannot be equal to ±2, ±1. This one for sure, writing it in intervaltation is kind of crazy because I've got so many different sections to have. Let's see. We'll go from negative infinity to -2 first, then -2 to -1, -1 to 1, 1 to 2, and 2 to infinity. I think that set notation is often much easier for writing the domains of these. Let's look at the graph. As we suspected, the graph of this is pretty complicated. We've got 4 asymptotes happening. We've got a lot of different sections that are moving in all different ways, and the only way we can really get a good picture of this is to test the behavior near each of the asymptotes to determine whether the graph is going up towards positive infinity or down towards negative infinity. In a future graph, we'll go through all the components of graphing a rational function, but one like this has a lot of moving parts to consider.